Hi! We're looking today at area models and moving from some simpler area models to some more complex area models to help us understand multiplication. These are some simpler area models that we're familiar with. This one is 3 rows of 5. If I use an array to help me highlight that, I can see that 3 rows of 5 or 5 columns of 3. 3 times 5 is 15. So I know from my basic facts that this area model is showing 3 times 5 is 15, or 5 times 3 is 15. An array or an area model, they both show us the same fact. The second one gets a little bit larger, and I have 4 rows of 7. My array shows me 4 rows of 7. If I see it as an array, or if I see it as an area model, 4 times 7 is 28. How can I use this, what I know about area models in some simpler models, when I move to some more complex 2-digit multiplication? That's what we're going to look at now. I'm going to go ahead and show what we look at when we get to 2-digit multiplication. We like to look at maybe some set models initially. And I used my base 10 blocks, and then I drew what I saw. And I saw when I'm looking at a problem like 25 times 3 groups of 25, I draw that as a set model with 3 groups and each having 25. I drew the 2 taller rods that represent 10 and 5. So I have 25, 25, and 25. 3 groups of 25. 25 times 3 or 3 times 25. If I wanted to use the area model for 25 times 3, it would be this area model, 25 times 3, 25 times 3. It's 2-dimensional. I'm multiplying 2 numbers, and I'm getting a rectangle each time because I have equal units. This rectangle does not show all the squares as my previous rectangles did. And we're transitioning because as our rectangles get larger and larger, we get more and more squares. So we want to use what we know about math to transition as well and use our number sense. So if I know that this side is 25 or 25 columns of 3, then I can separate it off into 2 smaller rectangles and have 20 columns of 3 and 5 columns of 3. And if I want to, I can look at this as 2 smaller spaces instead of 1 large space. This space is 20 by 3 or 60, and this space is 3 because I know that opposite sides have equal length. I need to remember that about rectangles. This side has 3 and this side has 5. So my space here, 3 by 5, is 15. But what if I'm not quite ready to jump into this rectangle yet? What if I still need a little support and I want to be able to see those squares still? Let's look at what that model could look like. This is a model that is showing a 2-digit by 1-digit multiplication. In this case, it's showing us 25 by 3. So I have 3 rows of 25 or 25 columns of 3. 25 by 3. This is a familiar way we're looking at this, of seeing it. So if I want to look at that large rectangle and break it up into some smaller spaces, I can separate because I know that 25 is 20 plus 5. So I'm going to use 20 columns of 3 and 5 columns of 3. Then I'm going to look at those 2 spaces in smaller units. So this blue space here is 20 by 3. 20 times 3 using my basic facts. 3 times 2 is 6, but I'm 6 tenths here. So I have 60 as my value for this space. I don't want to count each one of those. I want to use what I know from my basic facts in multiplication. The area is 60. This space in the orange is 5 by 3. So 5 times 3 is 15. I know it's 3 because my opposite value is 3. So if the space of the orange rectangle is 15 and the space of the blue rectangle is 60. When I add those two together, I get the green space, which would have been the whole thing, which is 75, adding those two pieces together. This is only a small step away from the traditional algorithm or the method of computation that we're familiar with, that we will be using soon. But it's important for students to understand that these numbers have meaning, and that's why we use color coding. They are meaningful codes to show the value of the different spaces. And so coding is important, and labeling is very important, labeling the length of each of those sides. Because if we transition to larger numbers, we're probably going to want to transition to shapes that look like this. We're not going to want to draw in all of these, and we're not going to want to think of all these little boxes. We're going to kind of think in larger spaces, being more familiar and comfortable with our larger numbers. So that's what we're moving towards. So I can represent this 2-digit by 1-digit multiplication. I can also get a little more complex. I might want to choose to do a 2-digit by 2-digit multiplication problem, and I can still model that using an area model that shows all the squares. So as a transition point, I'm showing all the squares still to show that in this case, a multiplication problem that is 13 by 16 means that I have two dimensions. One dimension is 13, the other dimension is 16. I know that opposite sides have the same length, and so that I also know that this is 10 and this has a value of 3. So using what I know, I'm going to find out what the value of each of those smaller quadrants is. So if I look at this red space, it is 3 by 6 gives me 18. So it has a value of 18, and I color-coded here what my value was. So when I fill that in, I know that 18. I'm going to slide down to this one because it has a little bit larger numbers. I just wrote them a little larger. But the orange space has a value of 3 by 10, so it has a value of 30, and I color-coded that. My blue space, this length is 10 because it's the opposite side of this 10 length. So I'm not going to count each one of them. I'm going to use what I know about rectangles. 10 by 6. 10 by 6 is 60, so I have a value of 60 here, and I have a 10 by 10 rectangle here. So I have 100 here. Then I can easily see that if I want to know how much is in the whole, I just add together all the parts. I add the purple, the orange, the red, and the blue parts together, and I get my whole of 208. So 13 by 16 gives me a product of 208, and it's represented by this area model. I'll be able to move to area models then that do not have all of the squares in them, but are merely represented by the length of the sides and can be easily drawn by students, and it's actually easy to see what the values are and write the values in. We'll move from these modeling to traditional computation of 2-digit multiplication, following the complete understanding of how these